In this video, the acceleration due to gravity will be determined through multiple trials of dropping a phone at zero initial velocity. For the purpose of this experiment, the 5-Fox accelerometer that does not incorporate the gravitational constant will be utilized. Open 5-Fox on the phone to be dropped and choose the top option, acceleration without g. Absolute acceleration is chosen instead of linear acceleration for each axis to take account for the phone rotation mid-fall, possibly resulting in inaccurate values. A phone clamp is used to hold the phone in place at a certain height over soft padding. This will minimize human error from manually dropping the phone. Make sure that the height of the phone is appropriate and that the phone reaches maximum acceleration before making contact at the bottom. Note that the phone does not need to be placed at different heights for each trial, since only the period from during the instant the phone displaces far enough for acceleration to be near constant is analyzed. When ready, press play on the accelerometer and release the phone from the clamp. To analyze the graph of the absolute acceleration placed on 5-Fox, first pause the accelerometer and zoom in on the graph. Focus on the part for which the phone first deviates from having zero acceleration. If the graph shows a relatively constant value after an initial increase in acceleration, this shows that the phone has reached maximum acceleration during freefall. However, if no horizontal line is present, then that means the phone has not been given enough time to fall for it to reach constant acceleration. This would be required to readjust the phone at a greater height and try again. For the purpose of the experiment to determine gravitational acceleration, 20 trials were conducted with corresponding values selected from the period of constant acceleration on the graph. By averaging the values from the 20 trials, the acceleration due to gravity could then be obtained. The average gravitational acceleration is determined to be 9.79 meters per second squared. To calculate the absolute error, the average is taken from the maximum and minimum values. This resulted in a plus-minus 0.1 margin of error and thus a 1.0% random error. The gravitational value determined experimentally is thus 9.8 plus-minus 0.1 meters per second squared, compared to the literature value of 9.81 meters per second squared. The percent error is thus 0.2%, which makes this experiment highly accurate to the targeted value. The systematic error is the absolute difference between the percent error and the random error, which is thus calculated to be 0.8%.
This method of finding G encompasses a freefall of a magnet onto a phone. The magnetic roller was set up on the 5-Fox app on the phone and put directly under the stationary panel from which the magnet was to be launched. The app records the amplitude of magnetic field in microtesla, and as the magnet drops onto the phone, this amplitude of the magnetic field on the phone rises before becoming stable as the magnet rests on the phone. We will be using the basic kinematic equation V final squared is equal to V naught squared plus 2AD. Our initial velocity is 0 since our object is starting from rest position, so the equation we use to find acceleration due to gravity is A equals Vf squared over 2d, where d is the displacement of the object above ground, V naught is the initial velocity, and Vf is the final velocity. In this experiment, our independent variable was the height from which the magnet was dropped, and the dependent variable was the time interval between the magnetic field's amplitude from through the free fall. Our setup includes a magnet, a metal ring stand, and a platform. The measuring apparatus we used included a meter stick and the 5-Fox app. First, we secured the ring onto the stand at a chosen height. We press start on the magnetic roller and let it stabilize. Then we push the magnet from a platform onto the magnetic roller. Here under the graphs option on the 5-Fox magnetic roller, you can see the graph spike as the magnet falls closer to the sensor. We can find the time it took for the magnet to fall by analyzing the time between the initial amplitude to the final amplitude. These are our tables. This one is for displacements from 0.1 meters to 0.5 meters. Going from columns left to right, we have the times for each trial with the respective calculated value for the acceleration of gravity next to it. In the far right column, we have the average value for the acceleration of gravity from all 15 trials. We found the gravity values by using the equation that we previously derived. We found the final velocity by dividing displacement by time. These are the different times obtained through the 5-Fox apparatus. We found the final value by taking the average of 15 gravity values, which gave us a value of 9.8 meters per second squared. We found the absolute error using the Gmax minus Gmin over 2, which gave us an absolute error of 0.4 meters per second squared, thus giving us an acceleration due to gravity of 9.8 plus minus 0.4 meters squared. The percentage error is 0.173%, the random error is 4.08%, and the systematic error is 3.92%. Air resistance may be present in this experiment, but is ultimately negligible due to the relative low magnitude of the magnet's cross-sectional area. Otherwise, one error was human eyesight, which was a random error and could have skewed our results. We could have mitigated this error by proofreading and revising our results. In this experiment, we are trying to find acceleration due to gravity using freefall. We will be using the equation t equals v naught t plus 1 over 2 at squared. Our initial velocity is 0 meters per second since our object is starting from rest position, so the equation we use to find acceleration due to gravity is a equals 2d over t squared. As you can see in this video, t is the displacement of the object above ground, v naught is the initial velocity, and t is the time in seconds it took the object to fall from rest. Our setup includes a metal ball, a metal stand, balloons, a pin to pop the balloon, and a ring. The measuring tools we are using include a meter stick, a set square, and the Firefox app. First, we secure the ring onto the stand at a chosen height. This height is just a rough reference as we are actually measuring the height from the bottom of the balloon where the marble is sitting, and not the height at which the ring is secured at. Then we blow up a balloon, insert a marble inside it, and place it on top of the ring. We used a set square and a ruler to measure the displacement from the marble to the ground. Now we are ready to begin collecting data. We pop the balloon, which creates a loud sound that starts the timer. The marble hits the ground, creating a second sound that stops the timer. We conducted a minimum of 3 trials at each individual height, with 12 different heights in total. From this, we obtained data for displacement and time, which are used to find the value of gravitational acceleration. Additionally, on the left is an example value we got on Firefox for one of height at 0.994 meters. Using the equation a equals 2d over t squared, our acceleration due to gravity came out to be 9.905 meters per second squared. These are our tables. This one is for displacements between 0.095 meters to 0.994 meters. Going from columns left to right, we have displacement, displacement times 2, and then the uncertainty that comes with displacement, which is 0.005 meters. And then we have the time it took the metal ball to fall from rest in seconds. We also have the uncertainty for the time, which is 0.001 seconds. Then we have the time squared. Finally, we have the acceleration due to gravity that was calculated. We use Logger Pro to graph displacement squared versus time squared, and its slope gives us the value of g in meters per second squared, which is 9.9 meters per second squared. We found the absolute error using the g max minus g min over 2, which gave us an absolute error of 0.9 meters per second squared, thus giving us an acceleration due to gravity of 9.9 plus minus 0.9 meters per second squared. The percentage error is 1.40%, the random error is 9.04%, and the systematic error is 7.65%. In this experiment, we would find the acceleration due to gravity using the Firefox inelastic collision sensor. The inelastic collision sensor detects sound and makes a close estimate of the drop height and energy loss by looking at 3 consecutive bounces. The sensor assumes no air resistance, thus giving the height on the basis of a freefall. This is some of the data the sensor generated, giving the time difference from the initial time and estimating the initial height from which the ball was dropped. As we know the initial height from which the ball was dropped, we can use the simple kinematics equation h equals ut plus 1 over 2 a delta t over 2 squared to then derive acceleration due to gravity as ah over delta t squared, where h is the height from which the ball is dropped and delta t is the time it takes for the ball to bounce once. The independent variable in this experiment was the height of the drop, since the height was not measured initially before the trial. Random increments of height were taken and 15 different heights were tested. The dependent variable is the delta t and the time it takes the ball to drop from the initial height to the first bounce. The controlled variables are the balls used, since different balls will have different frequencies of sound as they drop. although this will not cause any major changes in the experiment. As such, in this experiment, the ball was maintained throughout trials. There were 15 different drop heights, and since no drop height could be exactly repeated, 15 trials were averaged, ranging from 0.05 meters to 1 meter. All the data was recorded on the Excel, and the acceleration due to gravity for each height was found. These values were then averaged, and the uncertainty was found. Since the uncertainty on the height and time values were very small, the uncertainty was tabulated using G max minus G min over 2. The value of the G found was 9.81 plus minus 0.02 meters per second squared, which is the random error of 0.2% and very accurate to the theoretical G value. The major sources of uncertainty in this experiment were the uneven surface of the ground the ball was dropped on, which caused the time to vary at times for heights between bounces. Since Firefox uses this time to find the initial height, this varied the initial height readings, giving us a slightly different value of acceleration due to gravity. This value, however, matches the theoretical value of G with a 0.2% random error.
Okay, so for this experiment, we will be finding the value of gravity using the period of a pendulum, which is recorded using the pendulum tool in Firefox. Now, the period of a pendulum is equal to 2 pi times the square root of length divided by G, where length is the distance from the center of gravity of the thing swinging on the pendulum and the end of the string. Now, if we rearrange this equation, we get gravity is equal to 4 pi squared times length divided by period squared. Now, to conduct this experiment, the phone was attached to a string, and then this was allowed to oscillate for a few seconds until Firefox could determine its period. This was done for 3 different lengths of string and 10 data points for each trial. Now, the length of the string was determined as half the length of the phone plus the length of the string. And the uncertainty for this is 0.001 meters because the meter stick that it was measured with has the smallest increment as 1 millimeter. And this is some sample raw data from one of the trials, and these values will be used for the future sample calculations. Now for calculations, gravity is equal to 4 pi squared times length divided by period squared, and this all goes on to 9.67 meters per second squared. Now the uncertainty for the period will be the maximum period minus the minimum period, or 0.02 seconds, and the uncertainty for length will be 0.001 meters. Now the uncertainty for gravity, because it's based on the period squared and based on the length, it will be 2 times the uncertainty for the period divided by the period plus the uncertainty for length divided by length. Now finally we have gravity is 9.6 plus or minus 0.3 meters per second squared, and this average value was determined by averaging all values for gravity, and the average uncertainty was determined by averaging all values for uncertainty. Now gravity is 9.6 plus or minus 0.3 meters per second squared. The relative error is 3% and the percentage error is 2%. So once again, we will be finding gravity using the period of a pendulum, and we will use this using the Firefox magnetic field sensor. Now, as previously derived, gravity is equal to 4 pi squared times length divided by the period squared. The length will be the distance between the center of mass of the pendulum and the end of the string, and the period will be the time taken for one oscillation. Now, to conduct this experiment, a magnet was attached to a string, and the string was hung from a fixed point as a pendulum, and this pendulum was allowed to oscillate with the Firefox magnetic sensor at the bottom of its arc. Now it was allowed to oscillate for a few seconds, and each time it passed the magnetic sensor, it reached one of these peaks. Since it passes the magnetic sensor twice for one period, the distance between these 2 times is equal to 1 period, or it can also be calculated as the distance between 2 peaks multiplied by 2 is the time period. Now the length is measured by half the width of the magnet plus the length of the string, with uncertainty of 0.001 meters because that is the smallest increment on the meter stick. This experiment was repeated 3 times, and this is a sample raw data from one of the trials. The time refers to the time of one of the peaks, and the period is calculated by one of these times subtracted by the previous time, all multiplied by 2. And the average period is calculated as the average of all these periods. The value 1.74 seconds was omitted as an outlier. Now, as previously established, gravity is equal to 4 pi squared times length divided by period squared. And when the values for the previous trial were substituted in, I got the value of 9.88 meters per second squared. Now, the uncertainty for period is equal to the maximum period subtracted by a minimum period, all divided by 2. So in the previous example, this would be 1.62 minus 1.54 all divided by 2, or 0.04 seconds. The uncertainty for gravity is equal to twice the relative uncertainty for period, because the value is based on period squared, added to the relative uncertainty of length, with the absolute uncertainty for length being 0.001 meters, based on the smallest increment on the meter stick. And all of this is multiplied by gravity to find the absolute uncertainty for gravity. Now, after processing all the data, we have the period from the 3 trials, and to find gravity, we took the average of all 3 periods and substituted into the formula gravity equals 4 pi squared times length divided by period squared. And the uncertainty for gravity was also calculated, as previously mentioned, to get gravity as 9.8 plus or minus 0.5 meters per second squared. And our gravity has been calculated as 9.8 plus or minus 0.5 meters per second squared. The relative error is 5.1%, and the percentage error is 0.16%. Okay, for this experiment, we'll be finding gravity by finding the period of a pendulum using the 5-Fox audio amplitude sensor. And as previously derived, gravity is equal to 4 pi squared times length divided by period squared, where length is the distance from the center of mass of the pendulum to the end of the string, and the period is the time taken for one oscillation. For this experiment, a phone was attached to the pendulum, and then it was allowed to oscillate over an audio amplitude generated from 5-Fox. Now, each time it passed the audio amplitude generator, it hit one of these peaks. And then the period of the pendulum would be equal to the distance between the 2 peaks. The length of the pendulum was calculated as half the length of the phone plus the length of the string, and the uncertainty is considered to be 0.001 meters because it was measured using a meter stick, and the smallest increment on the meter stick is 0.001 meters. And finally, the uncertainty for the period will be calculated later by taking the range of values. Now, the experiment was repeated 3 times, and this is the raw data from one of the trials. The period was calculated as one of the times subtracted by the previous time, and the time here refers to the time of the peak. And the period is the time it takes for one oscillation, and the average period is just taking the average of all of these periods here. And now, as previously established, gravity is equal to 4 pi squared times the length divided by the period squared. In this case, after the values have been substituted in, gravity is found to be 9.68 meters per second squared. Now, the uncertainty for the period is equal to the maximum period subtracted by the minimum period divided by 2, or in this example, 1.74 minus 1.62 all divided by 2, or 0.06 seconds. And the uncertainty for gravity is calculated as the value for gravity multiplied by twice the relative uncertainty for the period, because gravity is derived from period squared, and this is added to the relative uncertainty for length. Now, after all the data has been processed, it can be seen that the gravity is equal to 9.6, and the uncertainty is 0.7 meters per second squared. For the experiment, gravity was established to be 9.6 plus or minus 0.7 meters per second squared. The relative error was found to be 7.3%, and the percentage error was found to be 2.4%.
In this method, the acceleration due to gravity will be found using 5-Fox's acceleration without g sensor and a pendulum. In this equation, The period t is equal to 2 pi times the square root of L over g, where t is the period measured in seconds, L is the length of the string in meters, and g is the acceleration due to gravity in meters per second squared. This equation can be manipulated to solve for g, which equals 4 pi squared times L over t squared. This is a brief sketch of the setup. A phone with 5 Fox was used as the pendulum and was connected to a string of length L, which was securely attached to a lab stand, which will be shown in the video shortly. The positions of the phone in the diagram correspond to the maximum acceleration of the phone along its path. At the equilibrium position, which is straight down, the acceleration will be 0. This means that if an acceleration versus time graph of the phone is made, the time intervals between the maximum peaks will be the period of the phone's motion. Here the length of the string is being measured using a meter stick. In the equation, the length of the string will count this length as well as that of half the phone, as gravity acts on the center of mass. In this video, it can be seen that the phone is connected to a lab stand using a string. The phone is let go at an angle of 30 degrees and is allowed to oscillate for about 20 seconds before it's stopped. This is a sample graph from the third trial. At time equals 21 seconds, the phone is released from its initial position and allowed to oscillate. The period will be the time between two peaks on this graph. The times correspond to the time at which acceleration was at its maximum, as seen on the graph. The period was found by finding the time interval between two consecutive peaks on the acceleration versus time graph. The two crossed out data points are the outliers, as they don't agree with the rest of the data points. The length of the string in half the phone is 0.48 meters and was measured using a ruler which has an uncertainty of 1 millimeter. The average period was found by taking the average of all the values for period found in trial 1, 2, and 3, excluding the outliers. The acceleration due to gravity was found to be 9.9 plus or minus 0.7 meters per second, taking into consideration the sig figs on the uncertainty. The random error on this value of g was found to be 7.1%, whereas the percent error was found to be 1% and the systematic error was found to be 6.1%. The sources of error include the swinging and rotation of the phone as it moved due to the air resistance and instability of the phone as it was released. In addition, the ruler introduced some systematic error. To conclude, the acceleration due to gravity as found in this experiment is 9.9 plus or minus 0.7 meters per second squared, and the theoretical value is 9.81 meters per second squared.
In this experiment, we are using the pendulum to find the gravitational acceleration. The light sensor on a phone through the 5Fox app will be used to measure the period of the pendulum. We find that the pendulum is eligible for the simple harmonic formula period equals 2 pi square root length over gravity. We solve for gravity to obtain the formula gravity equals 4 pi squared times length divided by period squared. The effect of air resistance is minimized by dropping the bob at an angle of 5 degrees, consistently from the equilibrium for all trials. An independent variable in this experiment is the length of the string attached to the bob. The dependent variable is period. In order to detect and record the laser sensor to find a period, 5Fox is first opened and under the main menu, rod sensor is selected. We are given two options to display data, graph and simple. The graph option is used to find illumination versus time graph, which later helps to determine the period of each oscillation. The difference between two troughs with one trough in between is measured to be the period. We need three items: a phone with the 5Fox light sensor, a laser, a pendulum, a ruler to measure the length of the pendulum, and a protractor to measure the amplitude. We set up a pendulum with the laser on one side and a phone with the laser sensor on the other side. The light sensor is placed where the laser directly hits it. When the bob isn't blocking the laser, the line of the lux versus time graph spikes. When the bob is blocking the laser, the line of the lux versus time graph dips dramatically. Two equal length strings were used in a V-shape to ensure the pendulum's period would be accurate, described by two-dimensional simple harmonic motion. Measuring from the middle of the two strings' focal points to the center of the pendulum, lengths 0.295 meters and 0.159 meters were used. We set the initial amplitude of the bob to 5 degrees from equilibrium. When we let go, the bob blocks the laser as it oscillates. We're able to find the period by looking at the time difference between every first and third troughs in the lux versus time graph. In order to use the simple harmonic motions formula, we need the length of the pendulum and make sure our amplitude is less than 15 degrees. Then, we recorded data for a total of 112 periods and calculated their corresponding acceleration values. We found the period by looking at the time difference between every first and third troughs in the logs versus time graph. And to find the acceleration due to gravity, each period value was plugged into a simple harmonic motion pendulum formula with its corresponding length. From here, a truncated mean function was used to find a fair mean of acceleration values. This produced a result for each length, which we then averaged to find a value of 9.83 meters per second squared. This value is 0.2% away from the literature value. Some of this error can likely be attributed to differences in the gravitational field strength local to where the experiment took place. The standard error, a way to measure random error, was calculated to be 0.9 meters per second squared. This gave us our final gravitational acceleration value of 9.8 plus minus 0.9 meters per second squared. Finally, we calculated the systematic error to be 9%.
In this method, the acceleration due to gravity was found by using a Hooke's law and the equation of simple harmonic motion using springs of equal length but different spring constants. We would be using 5-Fog spring sensor to measure the period of each oscillation for each spring. The phone will be attached to the spring and it would oscillate giving a period. The displacement x would be found using a marker method system. Looking at the equations, in the Hooke's law, f is equal to kx, thus mg is equal to kx, and m is equal to kx over g, where k is the spring constant, g is the acceleration due to gravity, and x is the max displacement of the spring. Substituting this in the simple harmonic motion formulas for the spring, we get t is equal to 2 pi root m over k, which can be then simplified to 4 pi squared x over g is equal to t squared, where t is the time period of the spring to oscillate and x is the max displacement of the spring, giving us gravity value. To find x using the marker method system, we first need to find the equilibrium length with the mass system and the phone attached to the spring. Then by finding half the length of the line of the marker gives us the max displacement from the equilibrium position. To then find the x value, we simply need to add the equilibrium length plus the max displacement minus the unstretched length of the spring, which in this case was a constant of 36.5 centimeters. To record the data, 5 different springs of different spring constants were used, and 5 different trials where each spring constant were taken, thus giving a total of 25 different points. The independent variable is the spring constant, and the dependent variable is the period of oscillation and the max displacement x. The control variables were the initial length of the spring and the mass attached to the spring, alongside the markers. To collect the data, each spring was oscillated and the period was found using the 5-Fog app. The values calculated were then plotted onto an Excel file, and all averaged and then calculated. After finding the acceleration due to gravity for each spring constant, the uncertainty was found to be 0.2 meters per second squared. The major errors in this experiment come from the calculation effects from each spring oscillation, as the markers always did not give the extreme mass displacement of the springs. The measurement in the value effects was also plus or minus 0.5 centimeters due to the uncertainty given on the meter stick. The error due to damping can be ignored because the period was taken in the initial oscillations for each trial, although there is an error of 10% for the spring constants on their springs by the manufacturer. We found that the period across the trials for the same spring constant stayed the same. To reduce the errors, video analysis could be used, which was not allowed in this experiment. Finally, the acceleration due to gravity was found to be 9.8 plus or minus 0.2 meters per second squared, given a random error of 2.4%, and the systematic error was found to be 0.10%.
The acceleration due to gravity g will be found using a sound amplitude sensor by rolling a car down an incline. A cart rolls down an incline with an angle theta and an initial velocity of 0 meters per second, rolling down a total distance of d. The acceleration of the cart can be found using this kinematic equation, so that A equals 2d over t squared. In this FBD, we can see that the normal force acting on the cart is equal and opposite to the vertical component of the force of gravity acting on the cart. Therefore, the net force acting on the cart will be the horizontal component of the force of gravity. Therefore, it can be said that the acceleration in that direction will be g sine theta. If we equate these two equations, we can see that 2d over t squared sine theta will equal g. The independent variable will be the angle of the incline, and the dependent will be the time taken into travel from its initial position to its final position. The distance will be kept at a constant value of 0.6 meters. As the cart with a constant tone rolls down the incline, the highest audio amplitude will be when the car hits a sponge at the bottom of the track where the audio amplitude sensor is, and the minimum will be when it's at its initial position. Using this graph, the difference between the time it started rolling down and the time it reaches the sponge will be found. This will be used in the equations discussed previously. It's important to note that the fluctuations in the audio amplitude may be caused by the noise created when the car rolls down the track. The experiment was repeated for 3 different angles, and this is just one of the samples. The angle was measured using Firefox's inclination sensor with an uncertainty based on small fluctuations in angle when measured. The distance remained constant for all of the trials. Using the equation found earlier, we can now find a value for g. The final value for g for this specific trial was found to be 10 meters per second squared. The uncertainty on sine of theta will be the sine of the maximum angle plus the sine of the minimum angle divided by 2. The uncertainty on the time will be the maximum time minus the minimum time divided by 2, since there are a range of values. Therefore, the uncertainty on g will take into consideration the uncertainty on sine theta, on t, and also the systematic error presented when measuring the length of the track. This is the acceleration due to gravity as found in the first, second, and third trial, and these are their respective uncertainties. This value here is the average of these values for the acceleration due to gravity, and this average uncertainty is the average of these values here. Taking into consideration the significant figures of the uncertainty, the value for the acceleration due to gravity will then be 9.8 plus or minus 0.3 meters per second squared. The random error is 3.06%, the percent error is 0.089%, and the systematic error is 2.97%. The acceleration due to gravity as found in this experiment is 9.8 plus or minus 0.3 meters per second squared.
In this experiment, we are looking to find the value of the gravitational acceleration constant by using an accelerometer with an inclined plane. When the car is released down an incline, its acceleration will be equal to the acceleration of gravity multiplied by sine x, where x is the angle of incline. Assuming that the track can be considered to be frictionless, the track used for this experiment has been optimized to lower friction. Additionally, air resistance is being regarded as negligible over the time interval we'll be looking at. Firefox has a sensor which can track the acceleration of an object and a sensor which can find the angle of incline. The phone is put directly on the track, and Firefox can be used to find the angle of incline. Then, by placing a phone on the car and releasing the car down the track, the acceleration can be found using Firefox. In these two pictures, we can see the ramp and a car with a phone running Firefox secured onto it. We then took the acceleration values given for the y-axis, a pre-built feature in the Firefox app. We then repeated this 3 times for 3 different angles of inclination. This video shows one of the trials. Since there is an air resistance and it is a velocity-dependent force, it increases as velocity goes up. To have the minimum impact of it on our acceleration, we will have to take the acceleration at the beginning of the fall. We take the first highest peak as our acceleration since our car will first reach its maximum acceleration before getting affected by air resistance. From here, gravitational acceleration can be found by dividing acceleration by sine x, where x is the angle of incline. From here, gravitational acceleration can be found by dividing acceleration by sine x, where x is the angle of incline. The average value found across all the trials for gravitational acceleration was 9.56 meters per second squared. Our gravitational acceleration value was 3% away from the literature value. We also calculated a standard error of 2%, giving us a systematic error of 1%. With this, we got our final gravitational acceleration value of 9.6 plus minus 0.2 meters per second squared.
In this experiment, we would be finding the acceleration due to gravity using the 5-fox accelerometer sensor and an elevator. As learned in basic conservation of forces, as the elevator is going upwards, there is an acceleration upwards, causing the force net to be equal to force normal minus the force by gravity, which then gives the acceleration due to gravity as the mass times acceleration over the apparent mass minus the initial mass. This can be then seen as the elevator is moving downwards, seen through the FBD, that the acceleration is also downwards. This then causes the acceleration due to gravity to be written as the initial mass times acceleration of the elevator divided by the initial mass minus the apparent mass. To perform this experiment, 4 different masses were chosen, and 3 trials per mass were done, giving a total of 12 different trials. The electronic balance was used to place the mass and measure their changing weights as the elevator either accelerates upwards or downwards, giving their corresponding value of g. The independent variable in this experiment are the initial different masses and the different acceleration of the elevator measured by accelerometers. And the final mass is the dependent variable. The weighing scale calibration and the same elevator were used, although the elevator was highly inconsistent with the acceleration values. The data for the values was then taken by both the elevator accelerating upwards and accelerating downwards, and the corresponding equations were used to find the value of g. These values were then plotted onto a spreadsheet and their values were averaged. This provided a value for the acceleration of gravity as 9.8 plus minus 0.7 meters per second squared. The uncertainties come from the number of sig figs on the electronic scale and the uneven acceleration of the elevator. This also gives a random error of 7.14% and a relative error of 0.1%, which then gives a systematic error of 7.13%. This indicates that the main error did come from the mass values of the elevator and mass values of the electronic balance, giving faulty and wide range of data for the value of g.
Now for this experiment, we will use a pressure sensor 5-fox to find the acceleration due to gravity by measuring the pressure inside of a bag as mass is added on top of the bag. Now, pressure can be calculated as force per unit perpendicular area over which the force is applied, or force is equal to pressure over area. In this diagram, below we have a bag filled with air, a cardboard platform on top, and mass on top of the platform. Since the system is at rest, that means the force of gravity pulling the mass down is equal to the force created by the bag pushing it up. And that means the force created by pressure is equal to mg. So that means pressure is equal to mg over a. This can be rearranged as gravity is equal to pressure divided by mass times area. Now, if we graph pressure versus mass graph, then the slope will be equal to pressure divided by mass. So then gravity can be calculated as slope times area. Now for this experiment, the independent variable will be the mass added to the bag, and the dependent variable will be pressure inside the bag. Throughout the experiment, the area in contact between the masses in the bag will be controlled by using a platform to hold the masses. In addition, the masses won't exceed 2 kilograms to avoid warping the bag. The total air inside the bag, which affects the initial pressure, will be controlled using a heavy-duty Ziploc bag to avoid any leakage. So first we open the pressure sensor 5-fox and enable remote control, then seal the device inside a plastic bag. The bag will be blown up with air in a rectangular cardboard platform with known mass, which is determined using an electronic scale will be placed on top of the bag. Since pressure is also dependent on the area of which the force is applied, the edges of the area of contact between the bag and the platform will be marked with a Sharpie. And since the area of contact is rectangular, it can be calculated as length times width. Then one by one, individual masses with known mass, also determined using electronic scale with uncertainty of 0.01 grams, will be placed on top of the platform of the bag. This is done gradually because it takes time for the pressure sensor and 5-fox to recalibrate. And using the pressure sensor, the pressure within the bag will be determined depending on the mass upon the bag. This is a sample of one of the graphs created by 5-fox. Each of the peaks here corresponds to when new mass is added to the system. And there's a fluctuation of roughly 0.05 hectopascals, which will be considered as the uncertainty for pressure, which will be represented in the error bars of the graph. This experiment was repeated 3 times, but the sample raw data will be taken from one of the trials. Now, the uncertainty for the length is 0.005 meters, or half a centimeter, and this was chosen because when comparing the length of cardboard in contact with the bag When there's no mass on the bag and when there's the maximum amount of mass on the bag, there's a deviation of roughly 1 centimeter. So then the uncertainty will be considered half that, or half a centimeter. Now there's no uncertainty for the width because the width of the cardboard is always in contact with the bag, and the slope will be measured in pascals per kilogram. Now when the data is graphed in capstone, there's a linear relationship between pressure and mass with a y-intercept equal to the atmospheric pressure. Now the slope, which is in hectopascals per gram, to convert it into SI units, you have to multiply it by 10 to the 5. So the slope is equal to 0.00582 hectopascals per gram, or 582 pascals per kilogram. Now, even though the error bars are added, the line of best fits doesn't go through all the data points, which means that the majority of the uncertainty comes from the changing area as more mass is added to the bag. Now, gravity is equal to area times slope, or length times width times slope. For example, 0.14 meters times 0.12 meters times 581 pascals per kilogram. And this is equal to 9.78 meters per second squared. And since this is repeated 3 times, we have 3 values for gravity in the table below. And when you average the gravity, you get 9.9 meters per second squared. And when you average the uncertainty, you get 0.4 meters per second squared. And now the error analysis, since the majority of the error comes from the changing area, which is due to the changing length in contact with the bag, then the uncertainty is equal to the uncertainty for length divided by length times gravity, or 0.0505 divided by 0.14 times 9.78, or 0.3 meters per second squared. Now, the relative uncertainty is uncertainty of gravity divided by gravity, or 4.4%, and the percentage uncertainty is theoretical minus experimental value, all divided by theoretical value, or 0.78%. And now overall, the value for gravity is 9.9 plus or minus 0.4 meters per second squared.